Hello and welcome to lesson number 3 in Unit 2A of our grade 10 academic math class. This is solving for a side length in a right angle triangle. So just to recap, we spent the last 2 lessons going over the foundation of trigonometry, which is similar triangles and the things we can do once we know that 2 triangles are similar. From there we talked about how from a reference angle we can label all 3 sides of our right angle triangle, either hypotenuse, opposite, or adjacent. And then we talked about setting up the 3 primary trig ratios, which for the sine from that particular reference angle is the opposite side over the hypotenuse. For the cosine of that reference angle is the adjacent over the hypotenuse, and for the tangent from that reference angle, it is the opposite side over the adjacent. So now we're going to utilize this to find unknown values in a right angle triangle, specifically side length. So let's start right at the beginning. I've got a couple of these filled out, so you might want to take a moment now and just pause the video so that you can fill these out, have them in your notes, and then I'll talk you through them. So why don't you do that right now? Okay, you're back. Let's have a look at this first example. So in our first example here, we have triangle ABC. We're being asked to solve for x, accurate to 1 decimal place. So what you're seeing at the top here, and you'll understand it I think a little bit better once I actually do one with you in real time, I've written out the acronym that we use to memorize the trig ratios, the SOHCAHTOA. I've written this out and I'm going to be using it as a way to determine which of the 3 trig ratios I should be using to find the angle or to find the side length that I'm after. So let's start by looking at this triangle and realizing that we've been given a couple things. We've been given a reference angle, which I've circled, but here I'll just sort of color it in as well. So we're using 35 degrees. From there, we are able to label the side that we want, which is the opposite, across from our reference angle. And the side that we've been given is the hypotenuse, which is across from the 90 degree. So what you're seeing above here is if we want the opposite and have the hypotenuse, we're going to be looking for the sine ratio. So then I've written it out over here. The sine of our reference angle, 35 degrees, is equal to the opposite side, x, which we don't know, over our hypotenuse, which is 7. From there, we perform something, and let me just erase a little bit of this here. The idea is that there are 3 variables in here. The angle, the reference angle, and these 2 sides. Those are 3 items. But we actually only have 2 terms. We have sine 35 degrees as well as x over 7. So we have 2 terms. So this essentially is a ratio. And I'm going to do something to make it look, or a proportion rather. I'm going to do something to make it look a little bit more like the proportions we were using all the way back in lesson number 1. So now you can see I've written 35 degrees over 1. And what I'd like you to do, just as a proof of concept here, is to type sine 35 degrees into your calculator. Now, depending on your calculator, sometimes you can just type the sine button, which should be on your scientific calculator, followed by 35, and hit equals. And the number you should come up with is, I'll just write it down over here. You don't have to write this down, but just so you can reference it, 0.573576, etc. It goes on and on. So sine 35 degrees is a number, and I say that because it doesn't represent something unknown. It represents something that we haven't written out as a number. It just represents something that we sort of left in a more concise form, which is the sine of 35 degrees. But once we have that, what we can do is we can cross multiply. So once I've done that, I end up with x times 1, which gives me x, and 7 times sine of 35 degrees. And I type that into my calculator. Now something else I want to mention here, your calculator should be in degrees. And it's a little bit difficult for me without seeing your calculator to tell you how to set that. Most calculators in their display will have like a capital D or something like DEG showing up that will let you know that your calculator is in degrees. The reason I mention this is because there are on most calculators, there's 2 other types of ways to measure angles of rotation. One is radians, and you'll look at those in grade 11. And the other is gradients, which we won't look at all in high school. So we have to make sure that we are in the right measure of rotation, and we'll be using degrees here in grade 10. So you always want to make sure that your calculator is in degrees. So I type in sine 35 degrees times 7. So I'm typing it in, and I get 4.015, and I'm rounding to 1 decimal place, so that's 4.0. The 1 doesn't push it up, so it's 4.0 centimeters. All right, let's have a look at our second example. Again, I'll just take a moment to write it down if you haven't. Well, let's start at the beginning. Let's find the thing that we are after. So here's the side length that we are after. We've been given our reference angle of 56 degrees. So the side that we want is our hypotenuse, and the side that we have is our opposite. So once again, we're going to be using sine, since sine contains both the opposite and the hypotenuse as part of its ratio. So we're going to write that out again. The sine of our reference angle, which is 56 degrees, is equal to the opposite side, 9.1, over the hypotenuse, our unknown. Once again, sine 56 degrees is a number. When you type that into your calculator, you get 0.8290375, etc. So it's a number, and as with any number, we can write it over 1. So we've written sine 56 degrees over 1, and then we're going to be cross-multiplying. We end up with x times sine 56 degrees equals 9.1 times 1, which is going to be 9.1. In order at this point to isolate our variable, we need to divide both sides by sine of 56 degrees. Those sine 56 degrees have undone each other, and we're left with just an x. We have 9.1 divided by sine of 56 degrees, and that gives us 11.0 centimeters, and again we're rounding to one decimal place, so we are keeping our approximate sign right there. Hopefully this makes sense. Let's see if we can knock out a couple examples here, and you can watch me do it in real time and we can kind of work it together. I've just written the bare bones like SOHCAHTOA near every example, so let's start here. I'm going to start by identifying my reference angle. My reference angle is the one here that I've been given, 30 degrees. I could figure out what angle E is, but that's not necessary. I can just use the one I've been given, save myself a little bit of time. So from here, which sides do I have? Well, I have 29 meters, and that is across from my right angle, so that's going to be my opposite. And then the remaining value, the one that I want, is actually my adjacent value. So let's have a look. Adjacent shows up here in the cosine ratio and the tangent ratio. So we know that it's not going to be using sine. And the side that I have is the opposite side. So I'm actually going to be using TOA, will be the one that I'm after. So let's start by writing that out. So the tangent of my reference angle, the tangent of 30 degrees, is equal to my opposite value, which is 29, over my adjacent value, which is unknown. Again, I'm going to start by writing tan 30 degrees over 1. I'm going to set up to cross multiply. So I have x times tan of 30 degrees equals 29 times 1, which is 29. And now to isolate x, I'm going to undo the fact that it's being multiplied by tan 30 by dividing both sides by tan 30 degrees. I'm left with x equal to approximately, and now I just type this into my calculator, 29 divided by the tangent of 30 degrees is going to equal 50.22, so 50.2 meters. And that is my answer. Let's do one more of these here. Here we have example D. So let's start by identifying our reference angle. The reference angle, again, I'm just going to take the one that's been given to me. It's going to be 53 degrees. Now, which sides do I have? Well, I have the across from my 90 degree, this is going to be my hypotenuse, and the side that I have is going to be 12, and that is my adjacent. It is beside my reference angle. So once again here I'm going to be looking. I have adjacent, so that's these two right here. So once again I'm not going to be using sine this time. The side that I want is my hypotenuse, so not TOA either. I'll be using the cosine ratio. So let's start by writing it out. We have the cosine of our reference angle. The cosine of 53 degrees is equal to my adjacent side, which is 12, over my unknown side, which is x. From here, again, I'm going to write cos of 53 degrees over 1. And just to say it one more time, cos 53 degrees is a number. I type that into my calculator and it spits out a number. And as with any number, I can put it over 1. So I've written it over 1, and now I'm going to cross multiply. I end up with x times the cos of 53 degrees equals 12 times 1, so which is just 12. I'm going to isolate my x by dividing both sides by cos of 53 degrees. That's how I'm undoing the fact that it's being multiplied by x. Then I'm left with x is equal to approximately, and I'll type this into my calculator, 12 divided by the cosine of 53 degrees, and that's going to equal 19.93. So that'll just be 19.9, and my unit of measure is meters. So there we go. We're doing pretty good on time here. Let's see if we can crank out these last two, and we'll just get this all done in one video. So here we are, second last practice question. Let's start by putting our reference angle in. So let's use 40 degrees. From 40 degrees, the side that I have is going to be my adjacent side. And the side that I want is across from my reference angle, and that's going to be my opposite. So let's see, opposite, that's sine and tangent, so we're not going to be using cosine. The one that I have is adjacent, so we are going to be using TOA, or tangent, again. So let's start by writing that out. The tangent of 40 degrees is equal to the opposite side, which I don't know, over the adjacent side, which is 9. I'm going to write tan 40 degrees over 1, and I'm going to set up to cross multiply here. So I have tan 40 degrees times 9 equals x. And now I'm just going to type this into my calculator since x is already isolated on the right. So we have 9 times the tangent of 40 degrees, and that's going to equal 7.55, so 7.6 millimeters equals x. Okay, one more to go. Let's get it done. Hopefully this is making sense now. I'm still talking you through the steps, but hopefully they're becoming second nature at this point, or at the very least familiar and recognizable. So let's start by identifying our reference angle. Let's see what we have in here. So what we have here is the across from our reference angle, that is our opposite, and we have the one beside our reference angle, so that is the adjacent. And opposite and adjacent, again, you can start to phase out this SOHCAHTOA you're doing once you're really confident in selecting the appropriate primary trig ratio, but I have opposite, I want adjacent, we don't need those guys, we need tangent. So let's write that out. The tangent of 60 degrees is equal to the opposite, which is 10.4, over the adjacent, which is unknown. Tan 60 goes over 1, and we set up to cross multiply. We have x times tan of 60 degrees equals 10.4 times 1, or just 10.4. We'll isolate x by dividing both sides by tan 60 degrees. And we have now x is equal to approximately, and I'll just type this into my calculator, 10.4 divided by the tangent of 60 degrees, and that is equal to 6.00, so 6.0 centimeters is our final answer. And there you have it. This is using primary trig ratios and right angle triangles to find missing side lengths. Hopefully that's making sense to you. Crank out some of that homework. If you have any questions, reach out via email. You can talk to me in person in class. Otherwise, good luck with the homework, and we'll see you in the next lesson.